Welcome back. Let's talk about Chapter 2. I posted this document and I recommend that you print it out and follow along. This is the summary of the main concepts in Chapter 2, which should be familiar to you from your physics classes or any technical training some of you might have had. For example, I was in the military and they sent us to school for 6 months after the basic training, and I learned a bunch of stuff. But this is the classical theory presented from an academic point of view, like you'd get in your physics class. All right, let's go through it. So Ohm's law is V equals IR. So it's saying the voltage drop in a resistor. So you got a resistor, you've got a current going through this I, and then you've got a voltage drop that'll be across this resistor, and the polarity of the voltage drop will be this direction relative to the current. So the plus is always at the entry point of the current. So the resistor is fighting or resisting the flow of current, and it does that by producing a voltage. And there's also going to be some heat that's left, and I usually power that leaves the system in the form of heat, and I usually indicate that either with a capital P like this, or maybe a double line P, and then this kind of arrow showing that energy is leaving the system. Okay, there's that. The next rule is power law. So given we have P equals IV, and if you take V from Ohm's law and plug it in here, you'll get I squared R. And if you solve for I and plug it in here, you'll get V squared over R. So there's these three variations of the power law: P equals IV, P equals I squared R, and P equals V squared over R. Let's see, before we leave this, let's say a little bit more about Ohm's law. So V equals IR. If you plot or graph V versus I for a resistor, ideally you'll get a straight line, and the slope of which is R. But that in reality, it's not going to be exactly that. It's going to be kind of curvy, and then at some point it'll bend and break. But remember, we're just this math approximates the real world. It's just real world situation. Okay, so keep that in mind. Like I mentioned before in previous video, if you don't consider the real world simplifications of your model, you're not doing engineering. You're just doing math. Okay. Then we've got KCL, or Kirchhoff's current law, KCL. So this just says the sum of the currents at a node is equal to 0. Or I like to think about it like this: what comes in must come out. It's kind of conservation of matter, because electrons are matter. You can weigh them. They have a tiny, tiny weight, but they are mass. And let's say you've got 5 amps coming into a node. It's got to get out somehow, right? So 3 could go this way and 2 could go this way, or any combination, but the sum of what's coming out must equal the sum of what's coming in. What goes in must come out. It's conservation of matter, you can think of that, or conservation of mass. Okay, then there's Kirchhoff's voltage law, KVL. The sum of the voltages around a loop must sum to 0, or the energy sources must balance the loads. The sources must balance the loads. So you're powering some devices. You're getting energy into the system. Like you could draw it like this. So you've got a independent voltage source, for example, and then you've got a resistor. So there's going to be power coming into the system from outside to power this source. Could be the sun, could be nuclear power, could be burning coal, something like that. But you've got power coming in. Could be a guy turning a crank, on a generator with your hand. But there's power coming in, and then there's power leaving the system, and these need to balance. But the sources must balance the loads. But that's typically not how we draw it. But sometimes we draw it this way. Typically, we just sum the voltages around the loop. All right. You can think of it as conservation of energy. So in this little picture, I've got a 10-volt source, and then I've got a 5-volt being used at this load, and another 5 volts being used at this load. So there's energy coming into this source and providing 10 volts of potential, and then that 5 of those volts are dropped. I'm going the wrong way. So that really the current's going around this way. So 5 volts are dropped across this guy, and then 5 volts are dropped across this guy. So it's positive 10 volts, and then a 5 volt drop and a 5 volt drop. So the source must balance the loads. It's really conservation of energy, right? The energy supplied here at the source must balance the energy consumed at the loads. Okay, that's KVL. Okay, the next concept is valid source connections. So I like to cover up the stuff I'm not talking about sometimes. So there's the KCL one, that is hooking up current sources. So this is okay. So let's say you've got 5 amps coming out of this guy. So there's a certain amount of, coulombs coming out every second. 5 coulombs per second is an amp coming out of this guy and going into this node. And then this guy is also putting out 5 amps. And so they're happy, like this guy's putting 5 amps into this node, and this guy's taking that 5 amps out of that node and releasing it. And so this guy puts it out, and this guy takes it, and this guy puts it out, and this guy takes it. And they're happy, they can cooperate like that. But if you hook them up like this, here I have 5 and 10, which is bad, but even if it were 5 and 5, that would still be bad, because you'd have one guy trying to put 5 amps into this node and another guy trying to put 10 amps into this node, and they can't get out. Those coulombs cannot escape. Those electrons can't get out. So these guys are going to have an argument, and somebody's going to win, or somebody's going to lose, depending on whether you're an optimist or a pessimist. But and how that fight is going to go, it depends on the nature of these sources. If these were batteries, then they may reach some kind of a state where they just sit there. But if they're active sources, they may fight each other, and typically there's going to be a circuit breaker or something like that that's going to pop. But if you didn't have a circuit breaker, like this was like a motor or something, 2 motors trying to fight each other, bad things could happen. There's going to be heat, possibly smoke. Okay, so yeah, then there's a valid ways to hook up current sources, and there's invalid ways to hook up current sources, and it has to do with KCL, really, that there has to be a way for the stuff going into a node to escape, and everybody has to be happy. Okay, then there's KVL one, and this one means the energy around the loop must sum to 0. So let's look at this guy. This is a valid connection. So this guy here is trying to raise the potential by 10 volts, and this guy over here is trying to drop the potential by 10 volts. And so they're happy. This guy, so if you start out with 0 volts down here, you'd rise by 10, bring that 10 across, then you'd fall by 10, you'd back to 0, and everybody's happy. And these guys can coexist, But here, if you hook them up like this, positive to negative and negative to positive, this is bad. Here, if you start out at 0 volts down here, this guy's going to raise it 10 volts, and coming over here, this guy's going to raise it another 10 volts. Come back over here, it's going to raise it another 10 volts, and then another 10 volts, and another 10 volts, and another 10 volts, and it's just going to go around to infinity until you have infinite voltage, which is not a good situation. The infinite voltage is there's going to be a current associated with that. Things are going to melt, the wires. Okay, once again, in real life, there's fuse breakers, there's things like that, usually, but not always. Like this kind of thing, I did with my car once. When I was younger, I had no money, or very little money, and I drove a real beat-up piece of junk car. And I waited till things failed before they fixed them. And so jumping the car battery was not an uncommon experience for me. So this is the correct way to jump a car if you're using jumper cables. Imagine this was a battery over here and this was a battery. You want to go plus to plus and minus to minus. And then the batteries are happy with each other. But if you do this, you're going to get a very high voltage in here. You're going to get a super high current through there, and things are going to start melting. So I did this once in my car, and I noticed it because the battery started to boil. I had one of those translucent batteries. You could sort of see through it and see the water in there, and it was boiling. I was like, oh, that's bad. And so I grabbed the alligator clip on the battery with my hand, like a dummy, and burned my hand up pretty good. But that could have gone really bad. I mean, I've heard of batteries exploding. So be careful out there. But yeah. I think there's a scar on here somewhere still. Maybe not so much anymore. That was 40 years ago, 50 years ago. Anyway, so there's valid source connections for current, has to do with KCL. There's valid source connections for voltage, it has to do with KVL. All right, next concept is circuit models. Circuit models. Okay, it turns out, long story short, you have a little circuit like this where you can have measure the current going into this guy and the voltage across this guy. You're going to get a table of values. Okay, you could make a circuit that performs like this. See, so this is a black box. You don't know what's in there. It's a black box. You can't see inside. But you could get these measurements from the outside, V and I measurements. Okay, for any situation like that, you can construct various models inside that will perform like this, that will simulate this. So this could be a very complicated circuit in here. It could be a million components in here. It could represent lots of things. It could even represent a subdivision of houses that are getting power. Okay, but whatever it is, you can simulate this with a very simple circuit. And there's 4 different ones that you could use, and I've drawn them. Well, there's really 2. You could do this. Okay, and you size the value of R and V appropriately, and it will give you the VI curve down here that you've measured. This is called the Thevenin equivalent right here, named after some guy, Thevenin. And then for every genius Thevenin, there's another guy there's a lesser guy that wants to also be famous. Human nature. There's something called the Norton equivalent. You could do this, where you have a current source and a resistor. So typically we do the Thevenin because, I don't know, he won the fight for fame and glory. So what we're saying is you have a complicated circuit that you don't know what's inside, but you can measure the V and the I. And given that, we can build one of these that will do the same thing. Okay? That's a pretty powerful modeling technique, because what it's saying is that you can take a very complicated system, could be an entire section of the city, or it could be an entire piece of the microchip, whatever, and model it with this tiny little simple guy. And that's a very powerful modeling technique for simplification. Okay? That's the idea of circuit models. So this is presented in chapter 1. It seems trivial and kind of a little bit pointless, but it's super important. All right. The next important concept in the chapter is this power stuff. So you're gonna have power sources and then loads. You're gonna have things supplying energy to the circuit, and then other devices taking energy out of the circuit. And we need a convention, basically. So this is the way I think of it. For any device, there's going to be these two polarities. There's going to be the current direction. Sometimes I use the term polarity for current direction. Like I say the current polarity, but really it's the current direction. And then there's this voltage polarity. Okay, so if it's a source, then this will be the situation. That is, the current will be entering the device on this end of the arrow and then leaving on this end of the arrow. It'll be coming in with a certain potential, minus, and then coming out with a higher potential. So the way to think about it, you've got electricity or electrons coming through a device. They're coming out with a higher voltage potential. So coming out on the plus side. So we've put energy into the current stream. Okay, so it must be a source, because the device has these two polarity orientations. It must be a source. It's supplying energy to the system. Okay, if it has this orientation of polarities, that's why the term polarity is useful to talk about both of these together. If it has this orientation, that is, the current is coming out at the negative voltage terminal, then it's coming out with less energy. So that device must be absorbing energy from the current stream. So that's a load. So you can look at it this way. Here's a source, and we've used the symbol for a source because we know it's a source. But see, the point is sometimes you don't know. You know, sometimes there's a little box, you don't know if it's a load or a source. Okay, that's the point. But let's use a circle because here we're purposely using a source. So I use the little circle for, that's our symbol for dependent source, and give it a voltage, give it a current. So I have this situation up here, right? I have the current polarity, or current direction going this way to the right, and then it's coming in at the negative sign and coming out at the positive sign. So it's coming out with a higher voltage polarity. It's coming out with more energy, because voltage is associated with energy. Voltage is not energy specifically, but it's energy of charge separation. It's related to energy, okay? So if the current's coming out at the plus sign, that means that this circle here, this source, is providing energy to the element. Okay? So here's what I do. I'll write out power equals P equals IV is the formula I'm using here. P equals IV. So put the I in there, put the V in there. Or here I guess I used VI. Same thing. We get a value. And then I draw this. So it's 10 watts, that's the units. And then I draw this thing here. I draw the arrow and its relationship to the plus minus. And then that's my orientation for it being a source. So sources deliver energy. So we use the word deliver. I mean, you could draw the power arrow coming into this thing. I don't want to mess up my notes, but sometimes we'll draw the power arrow coming into this once we know that. Sometimes. Okay, here's a device that's a load. Resistors are always loads, by the way. So we're going to actually draw a resistor, but once again, sometimes we don't know what this thing is. But anyway, resistors are loads always. So draw the. So assume this guy has 2 amps going this way and then 5 volts going this way. So the current is coming in at the plus volt and coming out at the negative. So the way I think about it is the current is leaving this device with a lower potential than it came in with. So this guy must have removed energy from the device. So to do the calculations, use P equals VI. Put your values in there, 5 and 2, and you get 10 watts. Then I draw this, and I draw the arrow and then the plus and minus orientation next to each other, and then that matches my absorbed. That means absorbed, right? The only thing that gets tricky for this is the signs. So sometimes they want to be mean to you in the book and give you negative signs on quantities. So this negative 5 volts here, what does that mean? I mean, there is no such thing as negative energy, at least not in the classical physics. You know, Newtonian physics, energy is always positive. Starts at 0, goes up. Like Kelvin, you know, its temperature, it's a measure of heat energy. It starts at 0, goes up, right? There's no negative energy. Okay, that's classical physics. Now, I know there's some really weird modern physics where they talk about negative energy, but that's not in this class. Okay, so there's no such thing as negative energy. So what does negative 5 volts mean? It just means that the polarity is actually backwards here. It means that what's really happening is this is 5 volts, and this is the actual polarity, plus on that side and minus on that side. So why would they do this to you? Well, sometimes you don't know, and you're guessing. That can happen, and usually that'll come out in the answers. Then answers will be negative. But you know, here they're putting in a negative just to play with your mind and be mean to you. you know, make you struggle. But so how do you handle this? I just do this. I just put in the values as given, put in the quantities as given, put in the -5 and the 2. You come up with an answer, -10 watts in this case. Then draw the arrow and sign relationship. So the arrow's going this way and the sign's negative to plus. Okay, this thing here, this orientation means that it's absorbed. No, it's yeah, wait a minute. I'm sorry, this means that it's a source. The sources deliver energy. So what we're saying is there's -10 watts delivered, but there's no negative energy. You can't deliver negative energy, so flip the sign to positive and flip delivered to absorbed. Okay, so -10 watts of delivered is really 10 watts absorbed. Okay, and the fact it came up with, we started with delivered is because of this, these guys. This is the orientation for delivered. That's what I do, all right? Or if you don't like that, just redraw the circuit so that it looks like this. Okay, yeah, just redraw it and then do it like this with no negative signs. 5 times 10, or 5 times 2 is 10, and then this polarity here after you redrew it matches the load. So loads absorb power. So look, this is a circle and it's absorbing. That can happen. Let me squiggle this over here. So in fact, that can happen with actual sources. You can have power leaving this thing. So if this were the current and this were the voltage polarity, it means the current is coming in at the positive voltage and leaving at the negative, so the current is leaving with less energy. So this guy is using energy. So there's power or energy, both really, leaving this device. So this guy is acting like a resistor, which they do sometimes. You know that motors can be turned into generators, right? You know about regenerative braking on an electric car? So that's how electric cars increase their efficiency so you can get to work before they run out of juice. Is when you step on the brake, you're turning the motor backwards, right? When you step on the accelerator pedal in an electric car, there's a motor in there that power goes into that thing, and it's acting like a load, right? So so that's actually this situation right here, where this is acting like a generator, and when you're acting like a motor, you're putting power into the device. So the current could still be going this way, but it will yeah, I messed it up. It got confused. It's the other way around. Yeah, so a generator, you're putting power into the system from outside, like the wheels turning. Then that's turning the generator, and so the current is going this way. The current's coming out with higher energy, so you're putting energy into the system. A motor, the current's really driving it. The current's going this way. The current's going through this device, coming out of the other side with less energy. This is a load, and this is a source. Anyway, okay, so sometimes these little circly things can be loads or sources. Now, a resistor is always a load. Okay, so if you know the current direction, you know the voltage polarity always, and vice versa for a resistor. But for these guys here, you don't know. It could be they can be loads as well as sources. Okay, that's chapter 2. All right, now we'll work some problems. Thanks.